All right, let's start. Do you have any questions? All right. So, last time we were talking about chapter 3, conditional probability, 3.2, section 3.2, right? And so the definition, right, is that probability of E given F is P of EF over PF, right? If P of F pos positive, right? So this is to make sure that we don't divide by 0. And um, the interpretation is that if you have two events, E and F, then P of E given F, right, gives the relative weight of E with respect to F, right? So the interpretation is that you know that F has happened, right? With respect to that knowledge, how likely, right, or what's the likelihood that E happens as well. And so so that's one of the way, right, that conditional probability can basically asked. They ask you to calculate, right, P of E given F for certain events. But a I guess another way to use conditional probability is to use it in the reverse way, right? That basically, so this is called the multiplication rule, right? Sort of has very similar taste to the multiplication rule for combinatorics, which is that the joint events, probability of the joint event, the intersection, will be the probability of conditioning, right? The conditional probability of one on the other times the probability of the other one happens. And so I guess let's write down the more general version, right? So you can do intersection of n events, right? This is going to be En condition on all the previous ones, and En minus 1 condition on all previous ones, so on and so forth. E2 condition E1, E1, right? And even though maybe that the formula seems a little bit like, let's say, daunting, right? It is actually surprisingly maybe, right, that this is what we usually do. Right. Let's say without realizing, right, that it is conditioning, right? So basically, it's used a lot, but maybe, right, the user of the rule doesn't recognize that this is like conditioning that they're using. For example, right, let's say on the hat problem, right, the matching problem. Well, if you look at the probability, so that you let EI be the event that the ith person gets the right hat, right? Then if you look at the probability of EI, EJ, right? Which is probability that both like person I and person J getting the right hat. So there are n people total, right? Then I think many, right, will just give this answer. 1 over n times 1 over n minus 1. Well, how would they give this answer? They say, well, the first person can get the right hat with probability 1 over n. The second person can get the right hat with probability 1 over n minus 1. So multiply together, right? That's the answer. Well, that's correct, right? But I guess the justification behind this, right, is because this is probability Ej condition Ei times PEI, right? And which is 1 over n minus 1, right, for this one. Because condition on the ith person getting the right hat, then there are only n minus 1 hats left to choose from, right, out of which, right, the J person can pick his right hat with one possibility, right, 1 out of n minus 1. And PEI, of course, is 1 over n, right, like that. Okay. So, of course, this can also be done with counting. So this is conditioning. And this can also be done, right, with counting by realizing, right, that there's n factorial ways total of permutations, right, among n objects and assignments. And there's n minus 2 factorial ways when you fix the position of I and j, right? So this is done by counting, and it will give the same answer as this, right? So basically what I'm trying to say, right, that there are multiple ways to get to the answer of the same question. One of them possibly is via the multiplication rule, right, by conditioning. But what you must always do when you do calculate probabilities is that you must give a reason for why you answer this way, right? If you just do something without realizing the rule behind it, then even if your answer is correct like this, it's going to be just basically, I want to say is by luck. And that's not very good because on an exam, luck doesn't happen that often. And second, right, you would need, right, you must have, let's say, justification for your answer on the exam, let's say, to guarantee, right, that your answer will receive like full credit. Okay. I mean, depends on how you write the answer. If it's unclear how you arrive at the answer, or if it's just like agree, right, with the correct answer by accident, then you're not going to be receiving, right, full credit for that question, for example, right? So now let's go over, right, some problems to make sure that we get this right more deeply. And I guess maybe let's start with the first question on your homework, which is question 3.1. 2 fair dice are rolled. Find the conditional probability that at least one lands on a 6, given that the dice land on different numbers. Okay. So how do we do this problem? You should always start right with naming the event just so that it's clear what you're computing. So here, E, right, is the event that at least, right, one of them is a 6, right? And then F is the event that you have different numbers, right? And you're asked to compute P of E given F, which requires you to calculate, right, PEF and PF. So let's see, right, what's PF?
30/36.
Mm-hmm. What's PE? Oh, sorry. What would I say PE, right? It's PEF. What's the probability that one, at least one is a 6 and you roll different numbers? Ten over 36, right? Why? Because it's 6, 1, etc., right? Up to 6, 5. The reason is because you roll different numbers, so 6, 6 is not included, right? And then similarly, you can have 1, 6 up to 5, 6. So that's 10, right? Possibilities. Which is right, whatever. But so notice, right, that the 36 cancel. So a lot of the times, right, you see that when you do conditioning calculation, the sample size, the original sample size, right, of omega get canceled, right? But you still have to, or you should still use that as a middle step, right? I mean, although it canceled in a way, but it's kind of very bad business to get this number wrong because that just shows you just maybe not seeing what's going on or whatever, right? So, any question? All right. So let's revisit that question that we did last time, right, in the previous class. And to point out, I think no, this is question 3.6, right? So let's say an urn containing 12 balls, 8 of which are white, right? And let's say the other one, they don't say whatever was, let's say the other one are blacks or blue, whatever, right? 4 whites, 4 blacks. A sample of size 4 is drawn. So I guess let's distinguish this, right? A with replacement. So is without replacement, right? And then they ask the conditional probability of the first and third balls drawn are white, condition on that the sample have exactly 3 white draws. All right. And so what I want to do here is I want to redo this very carefully, right? And to point out different the ways to do this, you know, again, precisely. The reason is last time I think we did this kind of, let's say, hastily, right? It's at the end of the class. And when we do something quickly without setting up the steps, then mistakes can happen, right? Or things are not clear. So I just want to point out, right? I mean, for any kind of problem, to make sure that you get the right answer, you have to do them step by step, very carefully. And so let's start with A, right? So with replacement, meaning, right, again, that means you draw the ball and you pull it back in, right? So hold on. So let E, right, be the event. That the first and the third drawn are white, right? Let F be the events that exactly 3 whites ball drawn. All right. So our task, of course, is to calculate again PEF and PF, right? So I don't know. Let's see. With these kind of problems, it's first good for us to decide what the sample size is. All right. And sample size referring to the number of possibilities that things can happen in the original sample space, right? Omega. Okay, because F can also be considered as a sample size here. That's called conditional thinking. We'll discuss that a little bit in some problems. Like for example, right, when you do 1 over n minus 1 in the hat problem, you're doing conditional thinking. Because, right, instead of having n possibilities, right, for the ith person to choose his hat from, there's only n minus 1 possibilities because you know that the ith person already picked his right hat. So here, by sample size, I mean the original sample size, meaning that when you draw a, when you look at a sample of size 4 drawn with replacement, right, out of 12 balls, what do you think the sample size is? Because that's a very important question, right? That's something that we did not do last time. If you don't set this down carefully, then the way of our thinking will be confused, right, down the road. Anyway, right, what would this be? The sample sizes. I guess maybe I shouldn't use the word sample size. Maybe I should use the word the size of sample space. Was that what I said before, or the total number of possibilities, right? Something like that.
Well, choose 4.
That is with or without replacement. That's the mistake I made last time too, right? It's just language, but we want to make sure. 12 choose 4, is that with or without replacement?
I think it's with.
No. With replacement means what?
Without replacement, sorry. Yeah, 12
No,
to the fourth power.
I know. Yeah, right. You understand. It's very easy to confuse these things, but that's exactly it. That's why we need to be very careful, right? Yeah, it's 12 to the fourth, right? Because we take a ball out and we put it back in. So size always is 12, 12, 12, 12, 4 times, right? So 12 to the fourth. Okay, cool. So now once we decide that, so basically then, right, what we're looking at is 4 positions, right? 1, 2, 3, and 4, each of each of which has 12 choices, right? That's why we get 12 to the fourth. You see, that's why it's very important to set down the size of the sample space, okay? Because that dictates the mode of our thinking. We're looking at, again, 4 positions, each of which has 12 choices total. All right? And now, within that context, then, what's P of F? What's the probability of exactly 3 white balls drawn? Oh, sorry. So let's not even look at P of F yet, right? Let's look at number of ways for F to happen. So the reason, right, is P of F is whatever this number is divided by 12 to the fourth, right? That's the denominator. So we just look at number of ways for F to happen. What would that be? How many ways for us to have 3 whites in these 4 positions? It is 4 choose 3, 12 cubed times 8. Times 4, right? Sorry, not 12 cubed, 8 cubed times 4. Agree? Because, right, out of 4 positions, you choose 3 to be the white. The other one will be the black position, right? And then there are 8 possibilities for each of the white position, and there are 4 possibilities for the black position. Are we clear on that? All right. What about P of EF? So I guess we're gonna skip the number of ways as a question, right? We know that's what we're asking anyway. So what's P of EF? Again, right? What's P of EF? P of EF means we know this is a white, this is a white, and there are exactly 3 whites. What would that be?
Sorry, could you explain P of F again, real quick?
Sure. So again, right, this is a denominator, that's clear. Now, P of F means, so we want 3 whites, right? In these 4 positions. So, well, the first thing we should do is decide which of these 3 is white, right? That's 4 choose 3. Okay. And once you decide that, let's say this, and this, then each of them has 8 choices, right? For the white. And then the other one
Oh,
has
okay,
four
yeah,
choices
sorry,
with black.
sorry, yeah, I understand, sorry. Thank you.
Sure. Now, what about PEF? What would that be? So first and third are white, and we know that we need exactly 3 whites. What would that be?
Eight cubed times 4 times 2 choose 1.
Excellent. Right, that's exactly it. Again, it's the same reasoning, but now we do not have to decide this 1 and 3 positions because it's already right whites. So we only have to decide 2 positions here. Which one's white? And then 8, 8, 8, and 4. Okay. Any question? And then you see again, right? This washes out, right? To give us 2 over 4 choose 3, which is half, right? Because 4 choose 3 is 4. However, right, do not take for granted, right, this 12 to the 4th. Because without setting down the tone, right, setting down the environment that this is 12 choices with 4 positions, all the other calculations, right, will be conceptually confusing. Okay. So even though, yes, 12 to the 4th get canceled out in the final answer, setting it down is very, very important for the calculation, for the thinking. Any question? Now let me say something else, right? Here's a conditional thinking argument, which is basically not doing it with the original sample space, but doing with the conditioned sample space. All right. It's valid, but it's, I don't want to say it's more advanced, but it's a different way of thinking. You can do either one, doesn't matter. As long as, again, you're clear on what you're doing. But conditional thinking tends to be harder and tends to land you on the wrong answer. Okay, unless you know what you're doing. So what's conditional thinking? Conditional thinking is as follows. Condition on F, right? What does that mean? That you know there are 3 whites, right? There are exactly 3 whites in the 4 positions, right? That's what you know. What do you want? You want the first and the third position to be white. What's the probability of that? You know 3 whites, right? Out of 4. That's what you know, right? Now, how many ways can you have 3 ways out of 4? That's 4 choose 3 ways, right? There are 4 choose 3 possibilities. And here's the key. They're equally likely. And that's conditional thinking. You know that all 4 possibilities, namely 1, 2, 4, 1, 2, 3, 2, 3, 4. What else? 1, 3, 4. Right? These are all equally likely to happen. Okay? To have 3 whites out of 4. Now, what do you want? You want a white on the first and the third. How many of them are there? Here's a white on the first and the third. Here's another white on the first and third. So therefore, it's going to be 2 out of 4 choose 3, which is exactly that, 1/2. Do we understand? So this kind of cut through, right, the original sample space, and it strongly relies on you knowing that all these 4 choose 3 possibilities are equal likely. But let me say this, right? I want to mention this because it's totally a valid way of thinking. It's more advanced, and usually it's like the more sophisticated way of thinking. But just like any sophisticated tool, use it wrong, you're gonna get a wrong answer, or it tends to be used incorrectly by the inexperienced user. So for you guys, I would encourage this approach. It's slow, but it's safe. All right. This is quick once you're getting used to the mode of conditional thinking. So file this away and use it in the future, right? I mean, you can use it now, it's fine, but if you use it wrong on the exam, you're not gonna get any credit, okay? So, but if you use it right, fine. So I just want to mention this. All right, so now let's continue without replacing. All right, so first of all, again, right, the important question to ask, which we did not ask last time, is the sample space. What are we doing? What is the sample space and what's the size? When we, in this problem, we draw 4 balls, right? Out of this urn, look at this question. What's the sample space and what's the size? So someone mentioned 12 choose 4, right? Would this be the sample space and the size? Well, notice this is actually what we used last time, right? And this is what got me confused last time. The answer is I don't think this is the one I want to use. All right. The reason, and let me tell you what the reason is. The reason is because there's this language of the first ball being white and third ball being white. Remember, right, when you do 12 choose 4, you just grab 4 balls out of 12 balls without order, right? You grab 4 balls out of 12 balls without order. So within that way of thinking, which address, right, this, it won't address that. Does it make sense? And again, this is why probability may be hard, because you have to use the right calculation, the right context. Then you address every problem, every aspect of the problem. But if you use some tool that's, let's say, half related to a problem, but it's unclear if it addresses every single aspect, then you may get the answer, let's say, by luck. But you're not going to be able to understand the problem, and you're not going to be able to get the right question, the right answer every time, okay? So I'm not saying that 12 choose 4 is incorrect, but I'm just saying I don't see how 12 choose 4 would address the aspect of the first and third ball being white.
So would 12 choose 4 make more sense, just to clarify, when order matters? Or when order doesn't matter?
When order doesn't matter, right? So for example, some question like this, right? You pick 4 out of 12 balls. What's a probability that, let's say, 2 of them is white? Or even the exactly 3 white part, PF is addressable by 12 choose 4. But you understand what I'm trying to say? But when you say first and third balls being white, that's a little bit weird on how that will be addressed with 12 choose 4. Or at least, you know what, having said that, I will also use something like 12 choose 4, but in a different way. So what I'm trying to say, if we think of 12 choose 4 as choose of 4 objects out of 12, right? That's how we tend to think of 12 choose 4. Then order is not considered. Does that make sense? So it can address some kind of questions like probability of exactly 3 whites in the 4. Why? Because it will be something like 12 choose 4 at the bottom, and then 3 whites on, you want 3 whites, right? So out of 8, you choose 3, and out of 4, you choose 1. Does it make sense? Because this language does not refer to, let's say, first ball being white or second, right? When you say first, second, third, fourth, you are referring to order. Does it make sense? So that's what I'm trying to say. Okay, so how do we address this, right? How we address this is I think we still have to clearly see what we're trying to do. We still have balls laid out in positions, right? 1, 2, 3, 4, and if needed, up to 12. All right. The reason is, again, because we refer to first and third white, right, in our problem. All right, so what are we doing? Basically, we have 12 balls, right? 8 whites and 4 blacks. And we try to distribute them among these 12 positions. Correct? So we don't have 12 choices for each. We have 12 balls total, 12 objects total, and we distribute among these 12 objects, 12 positions. So what are we thinking of? And also, by the way, right, we tend to think that these 8 whites are identical and these 4 blacks are identical, right? We don't distinguish among the 8 whites and 4 black. So what are we thinking about? We're thinking about something like permutations when the objects within some groups are identical. Remember that topic? The number of permutations, right? Let's say blue, blue, red, red. Sorry, let's say, right? White, 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 black, black, white, black, white, that kind of thing, right? The number of permutations, but we don't distinguish among the members of the group, of the same group, right? So basically, the way I'm thinking of this is, right, I will distribute 12 balls among these 12 positions where I don't distinguish among the 8 whites and the 4 blacks. So yes, I will still do 12 choose 4, or let me just change a little bit. I will do, so the sample space, I will do 12 choose 8. It's 12 choose 4 anyway. But let me explain what my 12 choose 8 means. That means out of 12 positions, all right, I choose 8 to be my whites. The remaining to be black. You understand? For example, right, I choose this, whatever to be whites, and then the remaining blacks. In that way, right, I can tell whether the first and third are whites or not. Does it make sense? So it's still 12 choose 4, 12 choose 8, whatever, right? Doesn't matter. I can even switch to 12 choose 4 now. So I choose 4 to be blacks, right? But the meaning is slightly different. Right here, when we write 12 choose 4, we're thinking of picking 4 objects out of 12 in the sense of sample size being 4. You see, it's kind of a coincidence that there are 4 blacks and the sample size is also 4. But if you switch this number slightly differently, right? Let's say 5 whites and 7 whites and 5 blacks, right? then the same question can be asked, right? There's nothing that different about the question. I mean, like the answer will be different. But if you 7 whites and 5 blacks, and the sample size of 4 is drawn, then when you do 12 choose 4, just thinking of choosing 4 objects out of 12 objects. Again, it's the same. But my way of thinking would do 12 choose 5. Because out of 12 positions, I choose 5 positions with black. Does that make sense? So the 12 choose 4 here, and this 12 choose 4 is only the same by accident, because the sample size, the choose picking 4 balls and the number of blacks are the same in this problem. But my sample space has a different meaning from 12, this 12 choose 4. Do you understand? All right, so let's carry on. So out of this, what's P of F? So F means I want 3 positions, right? And now, of course, and now you want to focus on what happens in the first 4 positions, right? Because that's where the action is. You draw 4 balls, right? So you think of it as you draw turn by turn, right? You draw 4 balls. So this is your sample, right? This is the selection. What's the probability, or how many ways can you have 3 whites in this arrangement? Of course, keep in mind that you have to also talk about what happens here as well, even though you technically don't draw it out. Well, it's going to be what? Out of 4 positions, you still choose 3, right, to be whites. And then what? You have 8 positions left, right? And you have to choose how many to be whites now? You have 5 positions left, right? Agree? That will give you 3 whites out of 4 for the first 3 positions, right? This is 5 whites remaining in the last 8, and 3 whites in the first 4. And this will allow, you will say exactly, right, that you draw 4 balls, 3 whites, exactly 3 out of 4 in your sample. Well, PEF. So remember, right, EF means you have 3 whites out of 4, but you also know that first and third are whites. So if first and thirds are white, you don't have to decide its color anymore, right? So there are only one of the 2 left to decide. So that's 2 choose 1. And then the remaining 8, right, you still have to choose 5 to be whites, right, by 12 choose 4. All right. And so PEF, PE given F is PEF over PF. And that's again, you see, after everything wash out, it's 2 over 4 choose 3 or 1/2.
The 8 choose 5 and P of E of
Mhm.
P of that sorry. The 8 choose 5. That is regarding like everything after the 4.
Right.
Okay.
So that's correct. And that's a little bit weird, but it has to be there, right? Because even though we draw the first 4 anyway out, you still have, because right, that's dictated by our sample space. Our sample space arrange 12 objects into 12 positions, right? That's what this 12 choose 4 means. So therefore, we still have to, after we make arrangement for our first 4 positions, we still have to make arrangement for last 8 to make it, right, a complete arrangement. Is that okay?
So we still have to account for the ones that we don't draw from, even though just because they're included in the sample space.
Exactly.
Okay.
And that's why I say that the way you decide your sample space dictates your thinking. You see what I'm trying to say? Same as, right? And that's why the topic sample space in chapter 2 is important. It's not important as a concept, as in like the abstract concepts, because who knows, whatever sample space you use. It's important as, let's say, in application, because how you choose it, right? For example, like I said, if you choose 12 choose 4, as in the sense of choose 4 objects out of 12 objects, then I don't see how you can say this is a first ball and this is a third ball. And that's why I got confused last time, right? But when I try to arrange 12 objects into 12 positions, then I can exactly see where my first and third is. But if I do that, I need to take care of all positions down, right, from 1 to 12. All right, any other question? So last comment, right, is that this 1/2 is exactly the same 1/2 as the above. But one is with replacement and one is without replacement. So it might make you feel a little bit strange or interesting, right? Because why would they be the same? The answer actually is, yeah, they are the same because of conditional thinking. Notice, right, even though the way we calculate them is different, are different based on the sample space, because one is with replacement, one is without replacement. Right? Notice the way we lay out the problem is very different. Right? But the conditional thinking actually are the same, because the conditional thinking doesn't care, right? The conditional thinking cuts through the original sample space. It only focuses on what is conditioning on, which is having exactly 3 out of 4 white balls draw. And once you look at that, then it doesn't matter if you do it with or without replacement. These 4 possibilities are equally likely. And that's the rub, okay? With or without replacement, these 4 positions, 3 whites out of 4, are equally likely among each other. And therefore, right, 2 of them have 1 and 3 being whites. So it's 2 out of 4. Again, it's a subtle problem, right, to digest. And that's why I want to go through this problem carefully. There are many, many angles to go through. And I mean, I just encourage you, right, to work it out for yourself, to make sure, if you want to understand everything completely, see why, right, we do the problem in this way. Okay. All right. So let's continue on to 3.3, which is called Bayes formula. Let me see here. So this is the base of the same as the Bayesian statistics or something like that. Bayesian, whatever, in machine learning, blah, 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 that you see this day. Right, but of course we're not going that far. We're just gonna stick with the basic Bayes formula, right, in probability. But the taste is similar, and you can, if you understand this deeply, you can see why Bayesian statistics is sort of right using the same base, which is the last name of a person. So at the heart of it, basically Bayesian, let me just say, intuitively, you're trying to reverse the order of conditioning. All right, but it's much more detailed than that. All right, but if you have to capture Bayesian thinking in one sentence, maybe, all right, I don't guarantee it, but maybe this is one way of thinking about it. For example, right, if you could try to decide P of F given E based on P of E given F somehow. All right, and again, that's just an abstract question. The detail is as follows. But basically, right, suppose you have, you know, if it rains, then you will bring the umbrella with so much probability, right? So if rains, then you bring umbrella with, let's say, some probability. You can reverse the question and say, well, I'm not observing the weather, right? I see you bring the umbrella. What's the probability of it rains? Does it make sense? That kind of question. And once you put it that way, it makes perfect sense, right? If I know that you're very likely to bring an umbrella if it rains, then possibly I can conclude that if you bring the umbrella, then, you know, anyway, right? This is where it gets hazy because we need to put down the precise numerical answer. But that's the kind of like the question that invoke Bayesian formula, right? Bayes formula. All right, so in the details, I'm gonna write down a few things and then, you know, I want to tell you maybe a more practical way to do this. But basically, right? So suppose you want to compute PF given E, right? Then you just start with definition. It's P of EF, right, over P of E, all right, not P of F. And notice, right, the key is that P of EF still shows up in P of F given E because, right, intersection symmetric, right? EF and FE is the same thing as intersection. But once you have P of EF, then you can rewrite that using the multiplication rule as P of E given F times PF over P. And that's how you, at least at the most basic level, right, reverse the order of condition. So to find P of F given E, you do P given F times PF over P. And the reason, right, is they're both connected by their intersection. Okay, so far? All right. So the second, let me see here. A more elaborate development, right, of this formula is as follows. You can have P of, let me see here. F given E, right, is P of EF over P of E. And now P of EF is P of E given F times PF, that's fine, right? But you will also develop this PE as follow. First of all, right, PE is P of E intersect F plus P of E intersect F complement, right? Because F and F complement, the union, right, is the whole sample space, right? So this is E, this is F, right? So this is EF, and this is EF complement, right? But then you can also use multiplication rule on these guys to give you and this, by the way, actually is the base formula proper, right? What I was telling you above is more of the flavor, right, of the reversing conditioning. But this one is base formula proper, at least at the, the simplest level. Why, right? Because it asks you for probability of F based on E, and then it reverses everything and base E on F or E on F complement. All right. Now we'll do a few problems to demonstrate this language, but let me show you, right, what happens here. So let's see if this works. So here's E, and then F, and then F complement. Oh, sorry. So here's F, and then E, and then F complement, and then E. Let me see if that works. So this is the tree, right, demonstration or illustration. Of base formula. Right. So here, I do recall, right, that someone was asking last time that conditioning doesn't mean the order of time, I think, right? They say something happens before something, I believe, right? F happens before E. And I was saying, right, that I think that I discourage that way of thinking in general because that may not be precise, right? Because there's no time in general, right? Conditioning doesn't have to be attached to time. But here, conditioning does have this sense that when you do when you do F given E, then you are talking about if E, then F language, right? So try to kind of associate that into, right? So probability that you bring the umbrella if it rains, exactly, right? Condition, right? Condition on it rains, what is probably you bring the umbrella. So if, right, if it rains, bring the umbrella, right? So if you condition, right, whatever you condition on that, that's the one that's the if clause, right? So therefore, right, when you look at something like this, you can think of as a tree. If you go with F, right, so you start out with the starting point, you can either go with F or F complement. If you go with the F possibility, then you can also branch out with E or E complement. But if you go with F complement, you can also branch out with E complement, right? Now, then when you ask for P of F given E, what are you asking? What that means is you are observing that you're on either of this branch because you know that E happens now, right? And you asked, what's the possibility what's the probability that when I observe them on each one of these branches, that actually I'm along this branch, because you want F, not F complement. Does it make sense? That's what P of F given E is in terms of this tree. You know that you're along these two branches, because that's the only two branches that gives you the E outcome. And then you want to ask what's the probability that you're along this branch. And right, Bayes would say, well, that's going to be the relative weight of this branch, which is P of E given F times PF over the total weights of the two branches, which is that. Does that make sense? And again, right, this tree has that language. If E has the flavor of that language, if F, then E, right? If you approach along the F, after that you do this. So I tend to, right, when I do Bayes' formula, draw a tree rather than invoke this formula directly. And that's sort of one of the few times when I don't use a symbolic formula and I use more like a tree, a diagram approach. But this is as valid as that anyway, so. Any question? All right, so let's look at an example, right? What quiz are we on? Quiz 3, right? Um, so an urn contains 2 type A coins and 1 type B coin. So probability had, okay, so let me just not even write it down. If a type 1 type A coin is flipped, it's head with probability 1/4. If a type B coin is flipped, is head with probability 3/4. A coin is randomly chosen from the urn and flipped, given that the flip is head, what's the probability that is a type A coin? All right, so usually these problems are long to write down because there's so many scenarios, if this, then that, etc. But solving it should not be too long. All right, so again, right, you can take whatever approach you want, but for me, with this kind of problem, I will do a tree diagram. So I'm going to instruct you right along that way. You can do the formula approach if you want. But if we do a tree diagram, then can you tell me how the tree will look like? How will you start drawing the tree?
The first branch would be A and B.
Good. And then the second branch would be?
The heads and tails.
Correct, right. And then what do we fill in for the weights of these branches?
A would be 2/3.
And then from
B would
A
be
branching to
1/3.
head would be, yep.
Oh,
And A branching out to head would be?
1/4.
Correct, right? And this will be 3/4. Not that we need to
And
fill
then
out. This will be
3/4,
3/4,
1/4.
right? Yeah. And what's the answer here that we're looking for?
The heads column for A. The heads branch for A.
Which is 2/3 times 1/4, right?
Oh, I didn't get there yet.
That's fine. But it's just now multiplication. And can you say why multiplication here? What are we invoking?
Because it's the probability of it being heads and coin A.
Yeah, correct. But that's actually the multiplication rule, right? It's probability of head condition on A times probability of A, right? So that's exactly the conditional, that's the multiplication rule that we just talked about in the conditional section, right? Yeah. And then divided by 2/3 times 1/4 plus 1/3 times 1/4. Is that okay? Any questions?
Professor, I have a question.
Yep.
So
Oh,
why
sorry,
the
1/3 times 3/4. 1/3 times 3/4, okay? Yeah, go ahead.
so why the probability of A is 2/3?
Oh, because of this language, right? 2 type A, 1
So
type B.
oh, so two type. Okay.
Any other question? All right, let's do one more. This is question 3.13. All right, which says, again, these are questions that are long to write. So I want to try to just write the abbreviation of it. So someone is trying to take 3 exams, okay? In the summer. So first exam in June. If passed, then taken second in July. And if passed, then third in August. Oh, sorry, in September. Doesn't matter. All right. So 3 exams, you have to pass, right? The previous one to take next one, right? I guess that's what it says. Yeah, it also says if fails, cannot take the others, right? That's so probability that she passed first is 0.9. Probability pass first, sorry, pass second. Of course, you see now, you cannot write down probability of passing the second alone. You can, but is this 0.8, okay? And probability, sorry, pass second, right? Probability of you pass a third, condition and pass first two is 0.7. All right. Question A, ask for probability that she pass all three. But maybe let me ask this. What's the probability she passed the second exam? This is not in the question, but let's just ask. Can we say that? Do we have enough information to figure that out? Or, right, let's do this as well. You know, again, right, of course, this is in this section, so you know a tree is in order. But in general, whenever you have to, if this kind of thing, then it kind of makes sense, right, to think of a tree. So what would a tree look like in this problem?
You
What
need
would a
to
tree look
start
like in
with
this?
the branches of if she passes the first exam and if she doesn't pass the first exam.
Correct, right? So first, and then not pass, right? First. And then pass second, right? Not pass second. Well, this clearly doesn't branch out anymore, right? And then pass third. Not pass third. Right? Like that. Okay. And then this is 0.9, 0.1, 0.8, 0.2, 0.7, 0.3. Correct? Now, just out of curiosity, right? Just so you know, when we don't branch out anymore here, does that mean that we don't have something like pass second and not pass second here? Oh, we do. Because, right, you know, somehow a tree is kind of symmetric. I mean, a tree doesn't have to be symmetric, right? In general, like this tree. But a tree in Bayesian thinking seems to be symmetric. Or not. I'm just posing a weird question. Can we branch out here as well? Regarding the second exam? Down here.
Wouldn't the probabilities just be 0 then? For everything after that?
Well, not quite. You because you have two possibilities, right? So the probability of pass second will be 0, but probability of not pass second will be 1, right? Given that you don't pass the first. Does that make sense? So it's not all
Yeah.
0, it's 0 and 1. So you can still figure it out, but it will be 0 and 1, meaning that those are things that you know what happens anyway, so you don't have to figure out the numbers, right? Same thing. Does that make sense? Cool. So yeah, let's see, what is this? So
Would it
you
just
see,
be
right?
0.9 times
Yeah, go ahead.
0.8?
Correct, right? Exactly. Right? Because that's the only one that she will pass the second exam. This she won't pass. Right? So it's 0.9 times 0.8. But technically speaking, right, this is also what? What's another way to describe this event? Pass second and first. Agree? Is it surprising? The answer is no, because if you look at the logic or the Venn diagram here, then you have the first exam out, and then the second would be inside the first, right? Because you have to, if you pass the second exam, it implies that you pass the first exam. Does that make sense? Or, right, let's put it this way. I just want to kind of make you recognize that language a lot of times is the most challenging aspect of probability, in my opinion, right? The probability of passing second, given the passing the first, is higher than probably passing the second alone. And this is about casual conversation. If you meet the person, you wonder, oh, what's the probability she passed the second exam? You're really thinking that she passed both. She passes both, right? Because otherwise she will not be able to pass second exam. So that's kind of a bit lower. But somehow it's like her friend tells you that she passed the first exam. You know that. Then the probability she passing the second exam, in your opinion, will be higher because she's already made it through the first stage, so to speak. Does that make sense? So even though the language is deceptively similar, they're not, right? They're referring to different things. All right. Any question? So part B, I guess, which is the first question in the textbook anyway. What's the probability she passes 3 exams?
Would that just be 0.9 times 0.8 times 0.7?
That's correct, right? Any question here? So the third question says, given that she did not pass all 3 exams, what's the probability find the conditional probability that she fails the second exam? What would this be?
So E in this case would be failing the second exam.
Right. So correct. But here, okay, that's fine, right? So you can do E is fail the second exam, and F be the event that did not pass all 3, right? But I would say that, again, in this context, when a tree is in the background, I'm just going to put it that way, then parsing it through the formulas, I believe, is harder than just look at the tree. looking at the tree. All right. Again, the reason, right, is because if you have to parse through all the symbolic thing, did not pass all three means a complement of blah blah blah, right? So I would, even though here this is the probably the only place in this course I think where I would skip the symbolic control of the problem in favor of the diagram control. All right. But yeah, this is exactly what you're saying, but I'm not so sure if I want to proceed using the symbols here. That's what I'm trying to say.
So would it just be 0.2 times 0.9?
I doubt. Maybe you're correct, but I doubt, because in this kind of question, there tends to be a over something. But let's see if you're correct. So why is it 0.2 times 0.9? Because you're looking at this branch right here.
Yeah, exactly.
But what's the meaning of that branch?
That they were able to pass the first exam, which allowed them to take the second one, which because they were able to pass the first, they took the second and then failed the second.
Right. So basically the probability that she passed the first but failed the second, right? But you did not take into account of what? Conditioning. Where is this in your calculation? You see? So now let's go back to the flavor of base. The flavor of base is what? The flavor of base is not about calculating what the probability you being along some branch. Base is more sophisticated than that, right? Because the probability being along some branch is multiplication rule, right? The flavor base is you know you're along some branches, and then you ask for the probability you're along a particular branch or so. You understand what I'm trying to say? That's conditioning. You're sub-selecting among the branches because you are conditioning anyway to begin with, right? So with diagram thinking, when you hear the word conditioning, you want to ask which branch or which branches am I along under that condition? Does that make sense? So what branches are we along with under this condition? We're along this branch, or this branch. See that? Did not pass all three. Could be one of those three branches. Yes. And the branch we're interested in is that one. So it's a relative weight of this branch over the three. Right? So the answer is what you said divided by 0.9 times 0.8 times 0.3 plus 0.2 times 0.9. Or let's do 0.9 times 0.2, right? And then plus 0.1. Do we understand?
Professor, could we also just do 1 minus our answer in B for the denominator?
Nope. Because 1 minus answer in B is, oh, sorry. For the denominator, I'm sorry, not the answer. For the denominator.
Yes.
Yeah. In fact, you can, if anyone has a calculator, maybe they can check that. I think that's exactly it. Yeah, I think so. It should be. But again, right? not to criticize your answer, it's correct numerically, but notice, right, I'm always advocating for beyond numerical thinking here, right? In the sense of this, I honestly don't see 1 minus this in the denominator here. Because again, right, notice my thinking is a tree thinking. I'm thinking literally of which branches I am along by conditioning, and then which sub branch I'm selecting, which I don't see why it would land me on a 1 minus something yet, right? But of course, I mean, with your observation, these two are related that way. But I don't think the 1 minus this would naturally show up when I work on at least this part in the tree thinking.
Got it. Thank you.
Sure. Any other question? All right. So, right, again, I hope these two will suffice for now for you guys to practice, right? We'll do more on a Friday. For now, I want to continue on to 3.4, independent events. All right. So, there are different definitions, and Ross, I think, uses a slight different definition, but I would define like this. Event E is independent of event F, all right? And this is just a notation. Let me just say EF are independent, right? This is an orthogonal notation. Just abbreviation because, writing independent a lot of times is tiresome. But, E and F are independent, right? This is just my notation means orthogonal. But because as you'll see, orthogonality has a lot of analogy with independence. But anyway, right? If P of E even F is P of E, all right? And like I said, depends on your angle. Some people will take this as a consequence of their definition of independence. Or I will take this as definition and derive the other one as a consequence, right? So the reason is I think intuitively my definition or this makes more sense. Now, of course, you guys know the other definition as P of EF is PE times PF, right? Some people will use this as their starting point and then derive what I say here as a consequence. But I will use this as my starting point and derive this as a consequence, all right? Let me explain. Again, I am very much aware that this is the popular, right? If not the most well-known, whatever that means, result in probability, which, like I said, I try to tell you on day one, is mostly abused. Because what does that even mean? So here, right, the reason why I define like this is the following. Remember, right, conditioning means the relative weight, right, of E, given that you know F has happened, right? And I have shown you, or I have tried to show you, or you have seen some problem where condition on F change the probability of E, right? Just think of like the example of rolling 2 dice, right? And if you know that the sum is a 5, then the probability that the first row is 6 will be 0, right? Because if the sum is 5, the first row cannot be 6. So in this sense, right, the result of the sum and the result of the first row cannot be independent, which is clear to anyone, right? Because, well, if your first row is high, the sum is high, first row is low, the sum is tend to be low, that kind of thing. And then you see independence exactly plays on that, because it says that E and F are independent if knowing F does not change how you view E, or the likelihood of E is not changed even in the presence of the knowledge of F. All right? And that's why I think this makes a lot of sense as the definition. I don't know how to interpret this. What does it mean
Is it-
to say that probability of, yeah, go ahead.
I was gonna say, is it possible to draw this on a Venn diagram, or that idea of independence?
No, that's exactly it. I don't see how to draw it as on a Venn diagram because a Venn diagram you see, I think, is more conducive to sum and subtraction. I don't think this Venn diagram demonstrate that more multiplication. Because right, how would you demonstrate? How would you illustrate something like numbers? Like, I don't know, right? So as far as I know, this is not demonstratable, if that's even a word, on a Venn diagram. I don't think so. Oh, at least I'm not aware of it. All right. So, yeah, right. So again, I know this is the result. I just don't know how to interpret it, right? The probability of the intersection is a product of individual probability. Fine. Doesn't mean anything beyond that. It's just a numerical result, right? This has more meaning. But anyway, right? Let's show why this is true, why this implies that, right? So P of E given F, right, by definition is PEF over PF. And if it's required to be P of E, right, by definition, then of course this implies that PEF, you just multiply back, right? Is that okay? So there, right? It's just a consequence, a simple consequence. Of course, you see it's really equivalent because this also implies back this way. My only beef, if you want to call it that, with starting here is I don't know what this means as a definition. I mean, definition can be whatever you want to be, but to me, definition should have some intuition behind it, okay? And last but not least, right, notice that if I do this definition of mine, then it lacks symmetry in some way, right? Because I say E given F is not same as F given E. This, if you use as definition, has symmetry, meaning that it says E independent of F is a symmetric relation, right? E independent of F is F independent of E, whatever. But you can also, right, take one more step to show that this is the same as P of F given E is PF given FE over PE, right? And because this is a product, right? All right. So in other words, if two events are independent of each other, then when you condition on one of them, doesn't matter which one, then the other probability doesn't get changed. Or the knowledge of one doesn't help you with the knowledge of the other. Okay. For example, again, just some mundane thing. If you toss two coins, right? The knowledge of the result of the first coin doesn't give you a better guess on how the second toss turns out. That's why you tend to say they're independent. Okay. But again, notice the independence here is a definition and not something that is somehow say, oh, I know the coin tosses are independent, right? So let me give you an example. Let's say you toss a coin twice, right? And assume that this is equally likely outcomes. Okay. Then the probability, right, of head and tail is 1/4, right? Which will be equals to P of head times P of tail. Why? Because P of head is P of head plus P of head tail, which is 1/4 plus 1/4, which is half. And P of tail, right, is the same thing. P of head, tail head. Sorry, P of tail here is a P of second tail, right? This is second tail. This is first head. So head, tail, plus P of tail, which is again, right, 1/4 plus 1/4 equals 1/2. Anyway, long story short, right? What I'm trying to say is, when you toss a coin twice under equally likely outcomes, then I can conclude that the events first head, second tail are independent based on my calculation. It's not an assumption. It's not because, oh, obviously somehow that the coin toss are equally like the coin toss are independent. You understand what I'm trying to say? So independence here is a consequence of the equally likely outcome assumption. All right. Now let's try another mundane example. So what quiz is this? Quiz 5. Let's say you toss a coin twice, okay? And let's say probability of tail is 1/6. Probability of head is 1/2. Probability of tail is 1/6. 1/6 plus 1/6 is what, 1/3, right? So I'm just confused. And what's the last one? 1/3 plus 1/2 is what? 5/6, right? Oh, no, 1/6. Hold on. Yeah, I want to change to something else. Let's say 1/4. So 3/4. 3/4 plus 1/6 is what? 24, right? 18 plus 4. 18 plus 4 is 22, right? Over 24, right? So 2/24. Whatever, right? I just assign numbers so they add up to 1. Is the event first head and second tail independent? I guess I should use the word are, right? All right. So what's the conclusion? So first head and second tail, P head tail is 2/24, right? What's P of first head? That's 1/2, right? Plus 2/24, right? Which is 12/24, so 14/24, right? P of second tail is 1/6 plus 2/24, right? So that's 6/24, right? Agree? Oh, am I right? 1/6 plus, which is tail plus, yeah. And so I hope, right, I don't even have to do it further. This times this clearly is not that. So they're not independent. All right. So again, right, it's a very mundane demonstration. But you see, right, if I twist these numbers to add up to 1, then they're no longer independent. So there's no God-given reason why the first toss and second toss are independent. No. Again, you could go with an assumption. That's your model. You say the first toss and toss are independent, and you assign the quality first toss and second toss. But notice that's an assumption. That's how you build your sample space. That's a lazy way, if you will, to build your sample space. Okay. A lot of times you hear people say like this: P of head, right, is little p, and they say independent toss. Right, independent. Yeah. So what they mean, let's say for the sample space of 2 tosses, right, is following. This is equivalent to assigning head tail to be, right, clearly P1 minus P. Tail head to be, what was it? 1 minus P times P. Head as P square. Tail as 1 minus P square, right? So the key is that it's equivalent, not that it's implied. Meaning, right, that you can prescribe this, and in fact, what you're saying is this, or you can prescribe this, and what you're saying is that. It's the same thing. So independent is not something that's so obviously given or whatever, or so obviously observed. No, it's basically just another way, a quick way, if you will, to assign, right, outcome probabilities, right? Because suppose you have 10 tosses, then you're not going to sit around and list all outcomes, right? Especially when they're not equally likely. So saying independent tosses is a quick way for you to get away with assigning probabilities. But that does, like, again, that's a model, right? That doesn't mean that it's so obviously true in real life or anything like that. If you want to test it out, you have to test it out with data. Okay. Any question? All right. So the next, so I think I don't have to do much problems here because a lot of problems are self-explanatory and they're kind of easy. What I want to tell you next is the concept of mutually independent events. All right. Or basically, it's just the word independent. So what do people mean when they say 3 events or more, right, are independent? You know, they could say this, or they can say E1, E2, etc. up to En are independent, right? What do they mean by this? The reason is this, right? You could easily think that, okay, let's move to this context, and then we're gonna go back to the case when n equals to 3. What it could mean is that PEIEJ is P of EI times P of EJ for any IJ, right? Question, is this enough? Or is this what should be meant when we say the events like this are independent? When you say n events are independent, is this what you mean? Is it what should be meant?
It could be similar to the inclusion-exclusion principle, where we had to go up to E1 to En to check all of them are equal multiplications in this case.
Yeah, right. I don't know what you mean. That's correct. You need to check the third layer intersections. right? And so in which case, if you have 3 events and this is it, because you only have a second layer and third layer. But in general, you have to check all kind of intersection to make sure that they split. All right. So basically, second layer, third layer, fourth layer, right? You know what I mean by fourth, right? Any n choose 4 combinations, right? They all have to split. So in other words, splitting at the second layer is not enough. Or what people mean when they say events are independent is all these ways. Okay, so far? Now let's try to explore the not enough part. What does that even mean? What it means is that we claim that there could be events, right, where this is the word they call it pairwise independent, right? There could be events where they are pairwise independent, but they're not independent in this sense. Is that true? If so, can we find an example of that?
So would that mean that like E1 and En could be independent, but they might be dependent with other things in the set?
No, we're not saying that either. We're saying that E1, En, E1, E2, whatever pair you choose are independent because the keyword is for all ij.
Oh, right.
But when you go down to, let's say, the third layer, then this equation doesn't hold, right? What you're saying is the easiest check because they're not even pairwise independent. What we're saying is there are events that are pairwise independent, meaning any pair you choose will split. But say you go to a triple level layer, then they don't split. Is there such a thing? Well, it's an interesting question to contemplate, right? Because you can try to come up with examples like coin tosses, or this kind of thing, and try it out. You'll see that a lot of things you come up with are just independent all the way, right? Meaning that just independent in general. You have a hard time coming up with events that are pairwise independent, but not independent in general. But there's such a thing, all right? This is a subtle concept, but this is why we need to be careful to lay it out all the way. Let me give you an example, right? The example is to give an urn that consists of 4 balls that are labeled 1, 2, 3, 4, okay? And we just pick 1 ball out of the urn, okay? I'll let E1 be the event that the ball is ball 1 or ball 2. E2 be the event that the ball is ball 1 or ball 3. E3 be the event that ball 1 or ball 4. First of all, we understand what this means, right? The comma here is an or, because I'm listing out the possibilities for this ball. Are we okay? So what quiz are we on? Quiz 6. Are DEIs pairwise independent? All right, let's check. What's P of E1, let's say?
One half.
Correct, right? Good. So that's the same as P of E2, E3, right? What's P of E1, E2? Is
1/4.
right. Is that clear? Because E1, E2 intersection is just one, right? 1 out of 4. Are we okay? And it's clearly, right, it's 1/2 times 1/2, right? Times 1/2. Correct? So they're all pairwise independent. Okay, so far? Okay, last question. Are the EIs independent? What's the answer? Now, what do we need to do?
No, because if we take the probability of all three happening, then we have 1/4,
Uh-huh.
but that's not 1/2 cubed.
No, you're saying something in the right direction, but what's probably all three happening? Oh, sorry, you said 1/4, right? Oh no, I
Yeah.
apologize. You're right. You're right. I'm wrong. That's correct, right? Because all three happenings is still one, right? Which is 1 out of 4. But you see exactly that is not 1/2 cubed. That's exactly correct. Sorry. Very good. There you go. Right. So this is a cute example, but important. So keep this in mind, right? This is one of the few examples I know that demonstrates that events can be pairwise independent, right? So it's kind of weird. Basically, it says that condition on E2, you don't know much about E1. It's the same. But if you condition, so this is pairwise independence. But somehow if you condition on, let's say, E2, E3, then that's not PE1. They're not triple independent. So they're not independent in general. So, all right. So this is just to show you the independence itself is a subtle thing too. It's not all like out there, like, oh, obviously things are independent, etc. No. Independence, I guess if I can give you one quick summarization of it, is that it must be verified with calculation and it must be done with careful definition. Okay. All right. Any question? All right. If not, I'll see you on Friday. If there's any question, I'll answer. Right. If not, I'll see you on Friday.
Thank you.
Sure.
Professor?